Now, let us see some applications where we can use Stefan Boltzmann's law. Now, suppose I want to determine the surface temperature of sun, then what could we do? So, number one, let us see an example. So, determination of surface temperature of sun. We want to determine the surface temperature of sun. So, what are the things we require? So, we are stationed on earth, we did not go to the sun. So, what are the techniques we can use with the help of Stefan Boltzmann law? So, you see, this is suppose earth, and here we have a source sun far away. This is a highly exaggerated diagram, and we receive solar radiation from this solar radiation here. Now, we assume the radius of earth to be RE, this distance between sun and earth be denoted by R. So, let us assume that the earth acts as a black body, or if we are interested, we can assume certain emissivity of earth. Now, what happens? The earth absorbs this radiation and emits the radiation. So, at steady state, the earth absorbs the radiation because of sun's incoming radiation, and then radiates according to its own temperature. So, at steady state, so the earth absorbs all the incoming radiation, and then it radiates, according to its temperature level. So, suppose the earth absorbs all this. So, this is at the steady state. So, the amount of energy received on earth. So, the amount of energy received on earth is equal to solar constant S into pi radius of earth's whole square, where S is the solar constant that is nearly 1.4 kilowatt per meter square. So, what is solar constant? It is the amount of energy, solar radiation per meter square on the surface of earth at noon. So, that means when the sun is overhead, per meter square how much energy we are getting on earth is solar constant. So, the total earth receives S into pi Re square of energy per unit time. So, total amount of energy received on earth, this is on unit time. So, this is what we get. So, now this is the energy. So, S into pi Re whole square. You see, pi Re square, the area, cross sectional area here you can see this much. So, this is the area which is receiving energy. So, this whole energy is distributed throughout. So, we get this energy, but the energy is radiated by earth uniformly in all directions. So, the energy radiated is sigma, area of earth is 4 pi radius of earth whole square into average temperature of earth to the power 4. So, this is pi Re square cancel. So, this pi cancel. So, S is equal to sigma 4 sigma Te to the power 4. So, now solar constant can be calculated, T earth is known. So, in this way the average temperature of earth also we can determine. Now let us see the energy. We want to know what is the energy radiated by sun. So you see here, whatever energy is radiated, it has to cross the spherical boundary here. All the energy radiated will have to cross this boundary. So suppose let the power of sun be P. That means the power radiated, the total energy radiated per unit time by the sun is P in all directions. So what we get here, so P by 4 pi r square, this is r distance, so P by 4 pi r square into radius of earth pi re square is S, that is the solar constant S. So we have pi cancel, so the power will be equal to 4 r square, solar constant S, this Re, this is pi cancel, so Re will be here, this is radius of earth, so this r square is here and radius of earth whole square. So this is the power radiated by sun. Now the power radiated by sun will be given by sigma T to the power T of sun to the power 4 is equal to 4 r square S by Re square. So radius of earth will be required here, and you can see this can further be simplified if one thing I calculate, how much solid angle the sun subtends on earth. So let us see one more thing, solid angle subtended by sun on earth. So the solid angle means, suppose this is sun and this is earth. So how much solid angle it subtends? This is d omega. This d omega is actually given by this 4 pi radius of sun whole square, this radius of sun by this radius r square. So now we have related the temperature of average temperature of earth to the solar constant, that is what energy we are receiving. Now let us see that how much energy we are receiving and how much part it is from what the sun is emitting. So the sun, so let the power emitted by the sun is P. So P, the power radiated per unit time, will be 4 pi radius of sun whole square sigma T sun to the power 4. Now this is P. So this is, let us call this as 2. Now you see, all the power radiated has to pass through the spherical region of which this earth is the center. So you see how much power earth will get. So this P by this power P by 4 pi r square is the amount of energy per unit area you are getting, that is nothing but the solar constant. So I can put this solar constant S by P by 4 pi r square, and this is this. But again I have to use this distance r from here. No need of calculating all such things. So this is, we will write this as 0.3. Next let us see that if we have sun here, this is sun, and far away at earth we observe that the solid angle it subtends is d omega. So let the sun subtends an angle and subtends a solid angle d omega. So, d omega will be this area, that is 4 pi radius of sun whole square, radius of sun, by this r square. So, you see this thing can be replaced by only the solid angle, which we can immediately measure from the surface of earth without any difficulty. From surface of earth we can easily measure this. Now, let us use these things to calculate the temperature of the surface of sun. Now, you see this S, so this is 4 into sigma T e to the power 4 is equal to S. S is nothing but P by 4 pi r square. So, again you see this is P. P can be written as 4 pi radius of sun whole square sigma T s to the power 4 by 4 pi r square. You see 4 pi cancel, this is r the distance between sun and earth. So, this sigma cancels, 4 T e to the power 4 is equal to, here sigma cancelled. So, 4 pi cancel, radius of sun whole square by r square T s to the power 4. Now, you see you can replace this quantity r s by r square as this quantity, that is in terms of solid angle will be d omega the solid angle by 4 pi surface of sun temperature to the power 4. So, we have surface of earth sun as this 4 into 4 16 pi T e by d omega, this is the fourth root of this T s. So, you see from surface of earth what we should calculate, what is the average temperature of earth that on earth we can measure, that is T e. Fourth root of 16 pi by d omega, d omega is the solid angle the sun subtends on us, that can be easily measured. This is T s. This comes out to be nearly 6000 Kelvin. Surface of earth is nearly we can say 20 degrees centigrade. The average is 20 degrees centigrade nearly. Now, let us take one more example. Now, suppose we have two plates, this one and this one. This plate is hot and maintained at temperature called T hot, and this is T cold. So, it is maintained at T cold. So, these are large plates closely spaced, and so heat flows in this direction at a rate, suppose I naught. So, I want to know that if I shield this by two black blankets that are parallel plates, then how much is the rate affected. So, the point is, if I shield it, so these are the T hot and this is T cold. Now, I have introduced two parallel plates, they are also black. So, when I introduce in between them two parallel plates, they are going to affect the rate of heat transfer. How they are going to affect the rate of heat transfer, that let us study. So, you see all the surfaces are black. So, let us see what is the initial rate of heat transfer. Initial I am writing here. So, this is initial and final. So, initial rate of heat transfer I naught is equal to, you see this is a black body and it radiates energy characteristic of its temperature level, that is sigma area T hot to the power 4, and it radiates energy characteristic of its temperature, that is sigma A Tc to the power 4. Now you see, it radiates according to its temperature, as well as since it is a black body, it absorbs this radiation also. So you see, it radiates more, absorbs less. What is this? It is absorbing more, radiating less, but by some mechanism its temperature is maintained Tc. So external something is going on, that is not shown. So the net heat flow is the algebraic sum of this, that is sigma A Th to the power 4 minus Tc to the power 4, this is 1. This is the rate of heat transfer that is taking place here. Now the problem is, let us see that if I have placed two blankets, two identical plates, then what is the new rate of heat transfer I? So previously it was I naught, now what is new rate of heat transfer? So now let this temperature be T1 and T2. You see, it radiates energy. How much radiates energy? Sigma A Th to the power 4, which is the characteristic of its temperature. What about T1? T1 also radiates energy in this direction, that is sigma its area T1 to the power 4. Now this has two surfaces, this side and this side, so it emits again the same sigma A T1 to the power 4. Now it has a temperature T2, it also emit according to its temperature value. Suppose I say it is sigma A T2 to the power 4, this is also black, this is also black, so it also emits in this direction sigma A T2 to the power 4. Since it has A area this way and this way, so radiation emitted on all sides. This is Tc, it also emits radiation sigma A Tc to the power 4. Now you see, now these are the thermal radiations emitted according to their temperature, that is given by Stefan Boltzmann law. Now at steady state the heat current is I. So actually at steady state the net heat current is I. So you see here, this I, something is going this way and something is going this way. So you see this I must be sigma, difference of this sigma A common, T hot to the power 4 minus T1 to the power 4. This is equation number 1. Come to this way, this is also I, that means I must be again equal to sigma, because at steady state same heat current should flow through the entire place. So here sigma A T1 to the power 4, sorry T1 to the power 4 minus this is T2, T2 to the power 4. Next come to this level, this is more than this, so net heat flows in this direction, again I, that is sigma A, this is T2 to the power 4 minus T cold to the power 4. If I add, you see T1, T1, T2, T2, so only TH and TC is left, this is 3I, implies 3I is equal to sigma A TH to the power 4 minus TC to the power 4, and you see, you recall this thing is nothing but I naught is equal to I naught, implies I is equal to I naught by 3. Thus by introducing two blankets we are able to reduce the heat rate of heat transfer radiation by 1/3. So this is how black blankets are used to protect the or decrease the rate of heat transfer. Now let us take one more example to show what is the role of a black body and how it absorbs, how it radiates. So, now let us take a spherical probe. This is a spherical probe. So, we have a space probe. This is a space probe. Space probe of radius r. Now, the temperature of the surface is here T naught. T naught is the surface temperature. So, now we have sent a deep spherical space probe for some long mission, and on the surface we have some electronic equipments, so that they will send radio signals and we can study what photographs they are giving and all such things. So, the electronic equipment must be heated so that they can work efficiently. They have some minimum temperature at which only they can work. So, if there is very cold conditions, they cannot work. So, inside this there is some nuclear matter we have has preserved it, which continuously produces heat and thus keeps this surface at a temperature T naught. Now, suddenly we realized that we want to increase the temperature and the space probe is in deep space. So, we can't do anything, we can't change the fuel. So, what we do? We cover this with a black blanket. We cover this with a black blanket such that this distance small x is very small. So, it is an exaggerated diagram. So, we have just covered it with a black blanket, which is black from inside and outside. Now, as a result of which we are able to increase the temperature of the surface. So, now let us see after what is the new temperature of the surface if that space probe is covered with a black blanket. So, let us find the new temperature of the surface of the space probe if it is covered by a black blanket, black from both side, inside and outside, black blanket of nearly the same radius. This is what we want to do. So, now you see, initially the power generated inside the space probe was sigma a T naught to the power 4. Now, that power never changes. So, the power never changes. So, nearly this is also r plus x. So, this will be now equal to sigma new area A into T to the power 4. But since A dash is also equal to A naught, this radius is so small that its area can be also approximately equal to A dash, implies new temperature this will be T will be equal to T naught. So, now this won't have the temperature T naught, now T naught will be the temperature of this surface. So, what will be the temperature T? So, now let us draw another diagram. So, this is my space probe, its temperature T, and let us exaggerate. This is the blanket cover, this is the cover, black cover. So, whose temperature is T naught? Now, you see the thermal power generated was P. So, P power is flowing from here, it is flowing always in this direction P, and it has to flow in P at steady state. Now, what it is emitting T naught, this is emitting sigma A naught T naught to the power 4 this way, and it is emitting sigma A naught T naught to the power 4. If it has temperature T, it has to emit sigma A T to the power 4. So, now you see here, you can see this surface here. Now, it is net heat flow is P. So, let us see this one, see the continuity of this, it is getting P and it is going P. So, this minus this. So, we have sigma A T to the power 4 minus sigma A T naught to the power 4 is equal to again P. So, we want sigma A T to the power 4 minus sigma A T naught to the power 4. This P is sigma A T naught to the power 4, that is sigma A T to the power 4 is equal to sigma A T naught to the power 4. Sigma A cancel. So, T is equal to 4th root of T into T naught. So, this is how T is equal to 4th root of 2 times T naught. Now, let us explain once more, keeping in mind that where the energy is coming and where it is going. This is what calculation tells. Now, this is the probe and this is the exaggerated diagram of this. So, this is actually small. So, you see here, this is the power radiated outside because of internal mechanism. At steady state, it should be P and it should be P. Now, you see, this is emitting a power P this way, and since it is black from inside and outside, and so it has to emit P this way. You see, this is P going, so it has to emit 2P this way. Now, you can see it is also at steady state. How it could be possible? You see, whatever it is getting, it must emit at steady state. So, you see how much it is getting? It is getting from here P and from here this P. So, this P and this P 2P. So, it must radiate 2P. You come to this, it is getting 2P from inside, and so it has to radiate P here and P here, so that at steady state its temperature is constant. So, this is how heat comes and goes, where it is absorbed, where it is radiated. Now, we can further study this. Now, this time not only n blankets, one blanket, now we have n blankets. So, if I put n blankets, what is the temperature of the space probe? Now, let us handle this. So, now you see here, this is my space probe and I require an exaggerated diagram because I have to put n. So, this is 1, this is 2, let us put this 3 blankets. Now, you see, these distances are so small that I can assume this to be 0. So, finally, temperature of this is going to be T naught. What was T naught? So, power radiated was equal to sigma A T naught to the power 4. So, T naught, this is P. So, now you see, this is at T. So, it is going to radiate power P outside as well as inside. Now, you see, this power must flow in this direction from all cross sections everywhere, because at steady state what is power produced inside must go throughout all cross sections. You see, this is P coming. Now, since the net flow is P, so it must emit 2P. Now, you see, if it is emitting 2P outside, inside is also a similar surface. So, it must emit 2P inside also. Again, this is P, so it must emit 3P, so that the difference is P, and so is this one inside. So, now you see here, let us check the heat balances. So, if it is 3P, again it has to emit 4P. So, now let us check the heat balance. So, on this surface you get P from here, 3P from here, 4P. So, you are emitting 4P. You see this point, at this point you are getting 4P from here and 2p from here 6p. So, you are emitting 3p and 3p. At this point, from lower one you are getting 3p and outer one p. So, 3p plus p 4p, you are emitting 2p and 2p. Here you see you are getting from 2p, so you must emit p and p. So, thus if there are n black blankets to cover, then the radiation emitted by the surface must be how much? So, this is 4p. So, it is n plus 1p. So, this is the total emission power rate of the radiation emitted by this. That is equal to sigma a t to the power 4, and n plus 1 p means sigma a t naught to the power 4 is equal to sigma a to the sigma a cancel. So, t become 4th root of n plus 1 times t naught. So, this is the new temperature of the surface of the space probe if we cover it with n black blankets. So, you see these are the different type of problems and usage of our Stefan Boltzmann law.